Alright, here we have one of these geometry questions that you need to solve using vectors. The diagram shows a cuboid whose vertices are O, A, B, C, D, E, F, and G. Vectors A, B, and C are the position vectors of the vertices A, B, and C respectively, blah blah. Prove that the diagonals OE and BG bisect each other. So the first thing we want to do is actually to place these vectors if they aren't already there, because this is what we're basing our entire problem on. That is going to be A, as the thing said. We have our C here and our B here. We're going to be able to express everything in terms of these. I got that the wrong way around. C and B. To visualize what we're actually doing, which we don't actually necessarily always have to do, but it's worth seeing once, is that we are looking at the diagonals. So inside the cuboid, we're looking at this thing here, and where it intersects BG. At this point here, I'm going to call that X. I think the book calls it H, but essentially we can use just the fact that it's a rectangle, because we know that, to figure out that they bisect each other. But one of the first things about vector problems is you cannot assume any of the geometric properties you've seen before, and we just have to prove it completely, almost algebraically, in terms of A, B, and C. Now, the difficulty is where to start. The first thing you want to see is essentially that X is where they intersect. I can express all of these lines except for OX, BX in terms of A, B, and C. So the first thing you want to actually write is that you don't know how far along OE X is, and you don't know how far along BG X is. So you're going to just say something like OX is equal to some unknown. Now, for some reason in vectors we use lambda and theta just to make things complicated. So we're going to say lambda OE. That way I know it's somewhere along there, but we're going to figure out mathematically that it's half. And then also BX is equal to, now we use mu because, again, just to make things complicated, BG. And I'm essentially going to try to prove mathematically that these are half each. Now, this will work with ratios as well if they need to be different. But yes, so I can express these two in terms of A, B, and C, which is what I'm going to do, and then we're going to equate the coefficients. So I know that OE, if we actually just start from here to there, OE is go across one, up one, and back one. So I can actually write that using the addition rule. OA plus AG plus GE. You don't actually have to go via this stage. If you're perceptive enough, you can see that that automatically is just A plus B plus C, which then tells us that OX is lambda times that. BX, again, is, no, sorry, not BX. We want BG, again, is the same kind of thing. We start at B, we end up at G, so we're probably going to go minus B plus A and then plus C. But you can use the rule for addition if you want to. You want to essentially go through all the vectors that we know. And we are, for some reason, we are allowed to use the fact that all of these are parallel and the same side length, but not assume any of the other properties. Plus AG, which then gives me, that's minus B plus A plus C. Now, this is useful because it allows me to express OX as lambda A plus B plus C, and BX as mu. And then I'm going to mix those around to make them more logical. That minus just goes there. The reason we do this So far I can't really do anything with this, but the reason we do this is we want to be able to express one same vector two different ways. I want to express, so for example, I'm going to choose OX, but I could have chosen BX as well. I want to express this vector here going directly from O to X, but also going via the other diagonal. So if I express OX here as OB plus BX, therefore, or just that is B plus lambda A minus B plus C. We can then actually write that as mu A plus 1 minus lambda B plus, sorry, not lambda, mu, plus mu C. And this is useful because these are the same vectors. So if I actually expand this one out to lambda A plus lambda B plus lambda C, what we are going to do is essentially say, seeing as these vectors are the same, each and every single one of the components or coefficients needs to be the same as well, which sets us up on the A, we're dealing with lambda has to be equal to mu. On the B, we're dealing with lambda has to be equal to 1 minus mu, and that's actually what's going to unlock this. It turns out C is completely redundant because lambda has to be equal to mu is exactly what we're going to see anyway. So it's actually, this third dimension doesn't actually change anything from the type of question that we would be solving in 2 dimensions. But we're going to look at these two and essentially solve those together. So by substitution, I can say that this gives us mu is equal to 1 minus mu, which, if I take that mu over to the other side, gives us 2 mu is equal to 1, which gives me mu is equal to 1/2. But then I also know that mu is equal to lambda, so those are both equal to 1/2, which means that if we go back to the definition, this right here, what I've just proven, is that OX is halfway along OE, and it's also halfway along BG. Therefore, just finish the question off with a conclusion sentence. Therefore, OE and BX bisect each other. So we're just always looking for a way to express one single vector via 2 different directions using 2 different unknowns to then solve the simultaneous equation. Voila.